SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. We had a brief look at the deposits, mineral deposits of important metals like chromium, platinum group of metals, nickel associated with mafic ultramafic magmatism, and we looked at the general characteristics, their tectonic affiliation, the age distribution, and got an overview, basic idea about these deposits. And as I explained, that there could be many ideas, many new ideas coming up because of many observational facts, many things which remain unexplained, or many new experimental results coming. They can always be looked at a higher level, but for this within this limitation of this particular lecture series, we looked at the general characteristics of these deposits which are associated with mafic ultramafic magmatism. Now we move on to an interesting class of mineral deposit which are associated with also ultramafic magmatism, but they generally are the rich sources of the gem or the precious stone, which is diamond. So we will move on to the diamond deposits which are associated with ultramafic rocks, and the diamonds are generally a very specifically associated with the type of rock which are the kimberlites. So have a look at them, the classification, diamondiferous ultramafic rocks. The diamondiferous ultramafic rocks are generally can be classified into three groups. The group 1 kimberlites, dominantly olivine macrocrysts with pyrope, diopside, phlogopite and statite and chromite. The group 2 kimberlites, dominantly phlogopite in olivine mica groundmass, and the lamproite, which are dominantly titanium bearing phlogopite, titanium, potassium ricterite and olivine diopside and cyanidine. So essentially the ultramafic rocks would be generated by the melting of mantle rocks, as we know, but these constitute a very special group of ultramafic rocks in having hydrous mineral like phlogopite, which is a biotite, and within them, and that is how it makes them to be a very special type of rock. And also they are special because they do sometimes contain diamond, and the occurrence of diamond in these kimberlites is very much in the form of they are very disseminated, their concentration will be far low, about hardly a few carats in a ton of rock. A carat is 200 milligram, and then more importantly they do have both the gem and the non-gem variety diamond, and the ones which are the gem variety, and depending on the high carat value they are very precious to us. They are present in many of the older cratonic areas of the world. We just have a look at this diagram which gives us an idea about the conditions in which the diamond might form. To note an important point here, the diamond crystals that we see within the kimberlite are not a product of crystallization from the ultramafic melt, because the diamond, as we know, is stable only at a very high pressure temperature condition, and we have seen phase diagrams like this. Like this will be graphite and diamond. So generally diamond will always be stable at very high pressure pressure temperature conditions, and if the conditions changes, the diamond can always get reversed to graphite. Now, this diagram essentially shows a very thickened part of the continent is a lithosphere, where a very thick continental crust is shown with this gray color, and the the graphite diamond step, the line, the curve is also shown with respect to the isotherms 900, 1200, 1500 degrees Celsius, and as you could see, the depth goes to as high as 600 kilometer below the surface within the mantle. This is the part of the upper mantle, and also we see the eclogite stability field. This is the stability field of peridotite, the Herzbergite and nanite, and from the diamond shape we could see here that within this region, which is essentially a reduced part in the mantle in the lithosphere, part of the asthenosphere, here this is actually the part in which the diamond is stable, because the zone below this is slightly more oxidized with the carbon oxide layer, and the fugacity of oxygen which is shown here, you could see that it is less, it is much greater than the phyllite magnetite quartz buffer, whereas the oxidation state in this region of the asthenosphere is FO2 is 10 to the power minus 2 to 10 to the minus 1 on FMQ. This phyllite magnetite quartz buffer, almost like 1 to 2 orders magnitude less in terms of the oxygen fugacity. So, that essentially helps the carbon to be present in the form of diamond in this particular region, and this essentially is the diamond stability field below which diamond is not stable. What is shown here in these black lines, the black thick lines, they represent the kimberlite in the form of pipes, which we will be seeing in a short while now. So, they forms in the form of dikes, or they move through, or they just intrude through, the melts are generated here, and the melts migrate through the crust and in the form of dikes or pipes rather, and they are exposed on the surface, and these are the kimberlitic melt, or the kimberlite the melt which is generated within these layers. When they move up, they are very likely to catch, or they have these diamonds as the cut off fragments and can carry them or transport them to the within the crust which we find them. So, there are many studies which is done on them. This diamond is found out to be older than the kimberlite, and there are many evidence which are there to suggest that the diamond which is present in this kimberlite pipe are not actually product of crystallization from the kimberlitic melt. Kimberlitic melt definitely has some, it generally comes from a carbon dioxide rich part of the mantle. This diagram shows something here, which is the gray part, which is known as the diamond window, and that correlates with what exactly we just have seen in the diagram, where we require a thickened part of the lithosphere, where the isotherm, they call the geotherm, should be shallow, like this dotted series of dotted lines over here are the geotherm in the lithosphere, continental geotherm. The lithosphere, this geotherm which is pretty shallow, which is about 35 degrees per kilometer, will be only possible when we have a much thicker crust above, compared to the areas where the crust is thinner, where the geothermal gradient is supposed to be much steeper. So, this is the diamond graphite stability field on the pressure temperature diagram, and the intersection of the pressure temperature, this diamond stability field with this geotherm, the geotherm shown on these four series of lines. This gray part is only the labeled as a diamond window, or this the areas or the region in which diamond is stable. And this is a typical morphology, typical shape of a diamond bearing kimberlite, which is this part is known as the diatreme, and this is the kimberlite brachia, and then it is extruded at the surface here. It is very interesting situation, because sometimes we call this as a representing something like a phreatomagmatic process here, because when this diamond bearing kimberlite is intruding through the crust, it could always heat up the shallow groundwater. So, here the depth is shown in terms of kilometer. This is 0, this is up to 2 kilometer depth. This is the top surface of the diet of the kimberlite pipe, which has a base in the form of the seal, and is pretty interesting and complicated in its subsurface structure. And the more interesting fact is that this such kind of kimberlite pipes, they occur in groups or in terms of in the form of swarms. Many such dikes occurring in any particular part in the crust, and this heated water actually causes the rocks to fragment, and so that is why the abrexia kind of a zone is very common to many of the kimberlites, and they are extruded at the surface with fallback material, and the alteration there are some later sediments which are also deposited here, some tufaceous or some kind of material, and these sediments also get fragmented and they fall back on this material. They do represent very interesting geomorphic features as well. Now, what could be basically be told about such a situation, that we get diamond in them. If the diamond is sourced from a very great depth, and it traverses through several hundreds of kilometers on its way up, and then encounters lower pressure temperature conditions, then it is very likely that the diamond would get converted to graphite in this process, and we will not be having any ground diamond available within these kimberlites, which does not happen. So, that led us to believe that these kind of kimberlite pipes actually move up very fast within the earth's crust. Sometimes the movement can be as fast as 70 meters per second kind of rate, which is calculated, visualized for the rate of ascent or the rate of propagation of such kind of kimberlite pipes. And so we will so this is how the situation with this kimberlite of the diamond from deposits. These deposits are plentifully available in many of the cratonic blocks, including the older cratons in India, in Canada, in Australia. Many of the famous diamond fields are there, like the Ecarte diamond field in Canada, the Argyle diamond field in Australia, and they are very rich sources of diamond. We will get back to this again when we discuss about exploration for diamond. Now, we move on to another class of deposits, which has to be of course included in this particular category that we are discussing when we discuss about the mafic ultramafic rocks, and they are the carbonatites. They are a very special type of magma. They represent a very special type of magma, a magma which is essentially having carbonate melt, and they give rise to rocks which are carbonates with calcite and dolomite, and they also do occur as pipes, steeply plunging stalks up to 3 kilometers in diameter, and these carbonatites they occur in many parts of the world. One of the two important occurrences that we could cite is the mountain pass in California, United States, and the Bayan Obo deposit in Inner Mongolia, which is one of the major resources. So, these carbonatites they are economically very significant. They contain very high concentrations of the metals, which are the light rare earth elements and the high field strength elements. The light rare earth elements are the lanthanum, samarium, neodymium, gadolinium, etc., with some of the high field strength elements also, and like some of the minerals they contain the carbonate minerals, carbonate and the phosphate minerals is the bastnasite, which is a lanthanum cerium carbonate with fluorine and hydrogen, this OH in the hydroxyl site, parisite, this calcium cerium lanthanum carbonate, monazite, which we all know it is a phosphate of thorium one of the major minerals of thorium. So, they come from these carbonatites. The carbonatites generally are a result of very low degree of partial melting of mantle rocks, where the mantle rocks is rich in carbon dioxide by some process, and the rocks melt at about 2.5 gigapascal, corresponding to 90 kilometer depth. And such kind of carbonatites, such kind of generation of this kind of carbonatite melt is usually expected where we have continental reef zones, like their presence in some of the prominent reef zones only has given this idea. This diagram, this figure is actually representing the mountain pass deposit, where you could see that it is one of the large scale ore from this particular deposit, which is mountain pass deposit within the gneiss country rock. What is generally observable is that they do have multiple generations of such carbonatite bodies present in them, and there are different, they can be differentiated into like monazite carbonatite, bastnasite dolomite carbonatite, bastnasite dolomite calcite carbonatite, bastnasite calcite carbonate. So, these they do represent multiple episodes of injection or the generation of this kind of pegmatite, this carbonatitic body. And interesting is that the ores in this particular class are clearly primary magmatic. They are crystallized from the magma, and there are differences, subtle differences there in the host ore minerals. In Bayaobo, it is an iron oxide, fluorite, aegirine, augite type of rock hosted within the larger carbonatite intrusion, and the carbonatites are of multiple generation, and rare earth element concentration up to 0.5%. The way the metal rocks melt in low degree of partial melting up about 3%, this can have a carbonatitic melt which could have about 0.5% the total rare earth element concentration, and when we get them in the deposit, they get further enriched to almost even going up to 2%. So, that must be, there must be some kind of differences in crystallization differentiation process which is responsible in making this or further enrichment of this rare earth element in them. So, that brings us to the close of our discussion on deposits which are resulting out of the direct orthomagmatic processes. Although in situations like what we just discussed in a carbonatitic in a carbonatite, it cannot be essentially called as a fully dry magma, because even in case of a kimberlite which cannot be also be called as a dry magma in the strict sense, because of presence of many hydrous minerals. And what we have seen in case of the carbonatite also, there are mineral phases which have fluorine and hydroxyl as in the mineral in the crystal sites. To make up some of the points, so generally whenever we are discussing about these deposits, it is the age distribution, the tectonic settings which becomes the important attributes of these deposits. In the ultramafic complexes, we have seen that any simple interpretation on the tectonic setup or the tectonic control of this mineralization does not seem to be very straightforward, which is true for cases that we have already discussed. And even in case of the the platinum group of metal enrichment in the sulphide phases, they are all controlled by processes which all sometimes seem to be pretty hybrid and not exactly a very simple sequence of crystallization evolution that is expected in any crystallizing magma chamber, controlled by many factors like magma mixing etc. coming in. So, magmatism is an effective, and what we have to sum up, we have seen that magmatism is an effective and an efficient mechanism of enrichment of many important metals, and also precious stone as diamond, which we can go on to even calculate by using simple governing equations, taking the distribution coefficient of metals between silicate melt and solid, or a silicate melt and a sulphide melt, and can understand the basics, or to make an appreciation as to why such kind of enrichment takes place. Although some broad generalization could be made for these deposits, deviation from the theme is a rule rather than the exception, because as we have seen in many such cases, we always see observations which are starting from the very situation in the chromite deposits. Many times the simple models fail to explain many features, and thus models need to be invoked for mixing of magma sources, tectonic environment, mixed tectonic environments like both rifting and the subduction type, and deposits which are associated with older greenstone belts are considerably modified. So, the in the very beginning what we discussed, that we do see present day ore forming processes in many well defined tectonic zones in the lithosphere, as expressed in the sea floor or in many of the continental interiors, rift zones and so on. The older ones, like we see in age distribution, all the magmatic deposits that we have discussed so far, bearing one or two of them, most of them are in the old Precambrian terrains, where they have undergone multiple phases of deformation, metamorphism, remobilization of the ore body, thus making things a little bit more complicated for explaining all those deposit formation through very simple process of magmatic differentiation and evolution. So, we had a brief overview of mineral deposits which result from the magmatic process, and we have restricted ourselves in the beginning to the orthomagmatic process, and magma, which are essentially to start with basaltic composition and a dry, and the mineral deposit formation in a broad sense could be explained by the process of magmatic differentiation, which involves crystallization to give rise to the different members in a basaltic magma, and also the exsolution of a magmatic sulphide component, which selectively enriches many of the important metals like the like nickel and the platinum group of metals. So, with this now we conclude the discussion on the magmatic deposits, the orthomagmatic deposits, and we move on to discuss the another important process, which is the sedimentary process, and we see that how we can discuss, or how the sedimentary process, in terms of its efficiency, how they are important in formation of the mineral deposits. So, we move on to sedimentary process and the resultant deposits. In the classification scheme that we proposed in the beginning, we broadly divided the sedimentary deposits into two classes. The deposits resulting from process of clastic sedimentation, that means the erosion and transportation of fragments of rock in form of clastic sediments, and deposition in depositional basins, which could be a marine basin or could be a intracontinental basin or somewhere in the continental margin. And then the other class, which are the chemogenic sediments or the chemical sediments, and we will first take up to begin with the deposits which are resulting from the chemical process, chemical sedimentation, and within this we have a very important class of deposits of metal, important metal, which is iron and manganese. Both of them are abundant metals. So, the major source of iron and manganese in the present day come from this type of ore deposits, which are arising out of the chemogenic sediments in ancient late Archean to early Proterozoic sedimentary basins distributed in many parts of the world, like the Superior Province in Canada, the Quadrilateral Ferifero in Brazil, the Transvaal supergroup in South Africa, the Singhbum Orissa iron ore craton in India, and there are other sedimentary basins like in the central India and the Basar craton, and one the most important and the rich one is the Hammersley basin in Western Australia. So, these are the examples in which we get prolific development of this kind of iron formations in these basins, which constitute the majority of the bulk of the iron ore resources of the world. A little less significant in this class are the ironstones, which formed mostly in the Mesozoic time. We will not be considering them in details because they are not resources of iron, they are mostly used for different other purposes. And then the Neogene manganese deposits, which are mostly in and around the Black Sea region in Ukraine. They also constitute a major manganese land based manganese resource of the world. So, we will first take up the Precambrian banded iron formation of the BIF. To begin with, when we are saying it is banded iron formation, it does not represent any stratigraphic unit as we know them formation, but it is actually used for denoting a type of rock which we basically name as banded iron formation. And such kind of banded iron formation deposits are invariably associated with also occurrences of manganese along with them. As we come to this Precambrian banded iron deposits, these banded iron formations, we can classify them to three broad categories: the Algoma type, the superior type and the Rapitan type. The Algoma type, they are associated with the old greenstone belts and they are the oldest, belonging to middle to late Archean. The superior type, which are mostly observed, they come from the type area in the Lake Superior region in Canada, and they are the late Archean to mid Proterozoic basins. And the Rapitan type also is from the Rapitan basin in Canada. They are the late Proterozoic or the youngest amongst the banded iron formation in the series. As far as these banded iron formations are concerned, they are definitely very interesting class of deposits, iron being one of the abundant metals, and also as we saw before, they do form, their deposits are huge in quantity, billions of tons. This photograph is from Hammersley basin, where you could see such type of iron ore is occurring almost like constituting the entire hill, and some such occurrences are very common in many parts of the world, including the iron ore craton in India. So, and this is a exposure scale photograph of the typical banded iron formation. So, we call them, the term banded iron formation has come from the very appearance in which there are iron rich and silica rich layers which are present in the ore, which you could see from the photograph taken from Hammersley basin or even on this exposure scale photograph. So, this is one of the curiosities so far as these deposits are concerned. So, these banded iron formations, they mainly they are the BIF. So, they occur in Archean and Proterozoic sedimentary basins in many parts of the world, as I just mentioned, and they constitute of many different types of ores, the way they are named in different parts. The way they occur in this kind of banded forms, they are known as the BHJ, or in the form of banded hematite jasper. The jasper is basically the iron rich cryptocrystalline silica. They are present in the form of BHQ as banded hematite quartzite. They could be as BMQ quartzite, and they are named in different they are called by different names in different parts of the world. For example, they are called itabirite in Brazil in the area of quadrilateral ferriferro that we just mentioned. What we see, the dominant mineralogy in most of the cases when it is a algoma type, the mineralogy is dominated by mostly magnetite, and in the superior type and rapitan type, the mineralogy is dominated by hematite. Maybe it has to, it basically because of the fact that the with increasing oxidation, the superior type and the rapitan type, by the time they formed, the partial pressure of oxygen in the atmosphere was quite higher compared to the time during which this algoma type was formed. And this algoma type which formed mostly as a part of the this greenstones, where we get a very good sequence of the volcanosedimentary sequence starting with very mafic high MgO rich komatiites to gave rise to the tholeiitic basalts and the chemogenic sediments, clastic sediments, and the bimodal volcanism and so on. So many of these members of this the lower member of this greenstones, they are associated with this magnetite mineralization in the form of this banded iron formation. So, we will discuss about this banded iron formation, their characteristics, the possible origin and many of their characteristics in the next class. Thank you very much.